Welcome to those of you who have had time to come and join us in person. Thank you. And welcome to those of you who've taken the time to join us online. We appreciate that. This is the Curriculum Studies class, Inquiry-Based Teaching and Learning. Students from the College of Education are going to give their presentations about what they've learned about inquiry-based teaching and learning through conducting a research experiment, primarily using CLS techniques, but not necessarily restricted to that. I'd like to start in a good way by acknowledging that we are on Treaty 6 territory and traditional homeland of the Métis, but each group is also going to give a more nuanced acknowledgement, so I'll just leave it there. So we will start each presentation on time according to what was advertised. And so if a group does end a little bit early, we'll just take a bit of a break for the next group to start instead of running ahead for everybody's knowledge. Please keep your questions until the end of each presentation. Thank you. With that, I will turn it over.
Thank you, Tracy. Hello, our group is called Why Are We Poison Mushrooms and So Should You? My name is Spencer Pitzel. This is Emily Colas, and this is Nathan. So we're going to open with a bit of a land acknowledgement of our own. We acknowledge that we are learning, that the learning and growth we experience happens on Treaty 6 land. This land is the home of the Cree, Dene, Blackfoot, Saulteaux, and Nakota Sioux, as well as the homeland of the Métis Nation. We affirm our commitment to reconciliation, both in our words and in our actions, personally and also in our pedagogy. We are all treaty people. We'd like to start by also giving a special thanks to Tracy, Anna Maria, David, and all the CLS staff here for all the generosity of their knowledge, support, and also their time. So this is what we're going to be going through, a roadmap of our presentation. We'd like to open with who we are and why we're here. So we are all education students. We all are nature enthusiasts, and we're all deeply passionate about science. And why we're here is to explore science through inquiry, also to grow our own personal pedagogy that we're taking into the classroom, and to share the learning that we've experienced with you all.
Thanks.
Yeah.
So now we're going to talk a little bit about inquiry, what inquiry is, and some of the benefits that we personally experience. So during our class, we talked a lot about inquiry. It's a teaching method that's learner-led. It's very engaging, as we'll jump into later. And it happens side by side, and it's multi-level. So it can be like a huge group project like we did that takes months, that's very open-ended, or it can be very, very narrow. Like, well, one example I've done with kids is there was kids kept eating snow at recess, and teachers kept yelling at them. And it was, well, why can't we do it? So then we took some snow, put it in a jar, melted it, and it was brown and disgusting. And then they all learned through their question that they should stop eating snow. Anyway, it's not unintentional. It's not streamlined, so it can go all over the place. It's not independent. We'll talk a lot about the group work that went on in this group. And it's not comfortable because learning is never comfortable. Yeah, so one of the big important parts that we learned from our project before we jump into it is how engaging the inquiry based learning style is. You get to do lots of experiential things, like we got to come here and actually do all this stuff. And it was interest-based, so Tracy let us follow our own interests. Our group was particularly interested in mushrooms. It took us a while to get there, but then we were really interested in it, and we did a lot of research that I know I personally never would have done if I hadn't been a part of this project. There's also a lot of real-world application of knowledge, which Spencer will get into very later in this, and this increased engagement gets students deeper into the learning, and when learning becomes hard and uncomfortable, it helps push them through it. Yeah, so for our project, we'll get to the poisoning part later, but these are oyster mushrooms. They're a type of mushrooms that eat dead wood. So these are older rotting trees, and these mushrooms are living off of them. So oyster mushrooms are all over the northern hemisphere. They're actually quite unique. They can live in colder temperatures. They've been around forever, and obviously the first peoples interaction with mushrooms, specifically oyster mushrooms. So these different groups of people are ones I could find in empirical research. So they're in like we're actually documented using them. So they're like in California and the Pacific Northwest and in BC. Although these mushrooms grow like all across the entirety of the Northern Hemisphere here and in Europe and in Asia. But these groups use them for like as a food source mainly. And so there's lots of different ways they could prepare them, just like any mushrooms you could at the store. So they were eaten, boiled, put in soups and stews, or even dried. And today they're frozen or canned or preserved. And lots of different groups with lots of different ways of preparing them. And the reason that I'm talking about them as a food source is because we specifically looked at mushrooms because they're really good at uptaking toxins. So one very important thing to notice is that I'm not advocating that any of you should go eat mushrooms and poison yourselves. Although there is this kind of a double-edged disclaimer because there's this really colonial idea that mushrooms are really all dangerous and you shouldn't pick them, you shouldn't eat them, you shouldn't anything. If you know what you're doing, you're going to be fine. Just like picking berries is very, very dangerous. If you don't know what you're doing, you could easily hurt yourself. Same with mushrooms. If you know what you're doing, as my grandmother who taught me how to pick mushrooms, don't put anything in your mouth that you're not 100% sure won't kill you. Anyway. So why do we poison fungi? During our research project, there was a lot of research. If you look at the citations on the bottom about how good oyster mushrooms are at uptaking toxins, specifically, we're looking at lots of different stuff like heavy metals, and that's what we will get into later. So this process was, I originally was interested in looking at lichen, which is a type of fungi, and looking at like air pollution because the way that lichen works is anyway, that's not important. I could talk about mushrooms all day. Emily was reading this book about mushrooms that she was really excited about. And Spencer knows a lot about bees. He's a beekeeper, but you can see by the picture, and was interested looking at the like bioaccumulation impacts on the colony. And so we kind of started looking at fungi and toxins more generally. And eventually got at a research question, which we'll get into later, but we're looking at specifically mushrooms and heavy metals. So during this process, we all had different skills, right? Like Spencer was a beekeeper and knew a bunch of different things. Emily has a chemistry background. And so this is actually Emily teaching me how to prepare a sample and clean things properly because I messed up the first one. So I'm watching her help me explain things, and that's what we found. That's one of our biggest takeaways from this experience in the class as a whole, was how each of us used our different strengths and brought that to the table, specifically in the project, specifically in the group work. And we're able to help and support each other and play our different roles in the group at different times. Towards scared children interests, eventually got even further. Remember how we talked about inquiry is this big, messy kind of all over the place until you get it directed down. So I have a lot of experience foraging mushrooms and using them as a food source. Emily has a chemistry background in environmentalism. And like I said before, Spencer's a beekeeper, and all of their nature enthusiasm and science knowledge brought us to our final point about microremediation. And microremediation is basically an environmental tool where you use fungus to degrade or isolate contaminants in the soil. So if you break down the word microremediation, the etymology of it, so myco is just Latin for fungus. Remediation is like remedy. Another way to explain remedy is to restore balance. So you're using fungus to restore balance to an ecosystem. And this is where our project was going. And like I said about the group work, another thing, this is, I was actually late to our beam time. And so this is my lovely group members helping me out because time management is not my forte. But like we talked about, all of our different strengths, we helped each other out. And Emily's going to talk a little bit more about this.
Yeah, so Nathan kind of touched on this, the fact that oyster mushrooms are found pretty much all over North America. I tried to find a distribution map that was, nice and neat, and I couldn't. It was pretty hard. So what I did was I went to iNaturalist. I don't know if any of you have heard of it, but basically it's a website. There's also an app where you, as the public, can go out and find different animals or different plants or fungi in this case and take a picture of it and upload it to this website and say, I found this here. And then it's kind of a public database on where things are. And so because it's from the public, that's why this looks so sparse. All these little squares are where oyster mushrooms were found in Saskatchewan. I just wanted to put this on here to show that there's like quite a range of oyster mushrooms in this province, up by Waskesiu Lake and then all the way down by Regina. So they're quite widespread. I think a lot of the times, even I had this idea that if I wanted to go like foraging for mushrooms or just see mushrooms, I had to kind of go up north into more like forested area. But that's not necessarily true. You can find them all over. So this is just from 1994 to 2023, which isn't that huge of a time scale. That's also why it's pretty sparse. But I just want to show the range in Saskatchewan itself. And then before we get into our actual experiment, just background information on mushrooms and fungi. So within life, everything in life is classified scientifically. There's like two big domains. In this case, well, sometimes there's three. I'm not going to get into that because this isn't like biology. We're just going to focus on this. Within eukarya, that's where we are. It's things that have a membrane-bound nucleus. You find Animalia, that's all animals. Protista, that's pretty much everything that doesn't fit in the other categories. Plantae, which is plants, and fungi, which a lot of people group in with plants. When you have mushrooms, a lot of people just group them together with plants. But they're actually an entirely different thing. Like they're totally unrelated. If you're eating them, sure, you could count them as your vegetable, but they're not. They're totally different, and they're in a whole separate group. So fungi are removed. I think that's really important to note before we move on. We are not dealing with plants when we are working with this experiment. We're dealing with fungi.
Yeah, so the way that fungi work specifically, not exactly like plants, but they're similar. So the mycelium here, these kind of root-looking structures, are what transports the nutrients around the plant, not the plant, transports the nutrients around the fungi. These little white spots up at the top are actually the mushrooms themselves. This is one organism. All those mushrooms at the top are the fruiting body. So if you kind of think of it like an apple tree, so the apples have seeds in them, and their whole point is to reproduce and make more apple trees. The similar way mushrooms have spores, and the whole point of the mushrooms, the part that you see, usually on top of the surface, the whole point is for them to make more fungi. And like I talked about, the roots and the leaves are to collect and transport nutrients. So they kind of look like roots. This is the mycelium that connects the whole organism together. And then there's the soil if it was a tree, but for mushrooms, they call it substrate, and that's just what it's growing in. That's its nutrients. Yeah, so the way that mushrooms work, like these oyster mushrooms, they, when they're feeding, they kind of do ingestion and digestion in reverse than people do. So if I ate something, I'd put it in my mouth, I ingested it, and then I'd swallow it, and then I would digest it with my stomach acid. Mushrooms are kind of reversed. They barf on their food first, so they release an enzyme that breaks down stuff externally, and then they suck it back in and they ingest those nutrients, which is why they're so good at growing through things like wood. It's also why they're so good at picking up toxins, since their enzyme, they're taking up everything, sucking it all in, and then that's why mushrooms work so well in their environment to break down things and put those nutrients back into the ecosystem for other things to use. And it's also why they're so good at taking up toxins, which is why lots of scientists are looking at them to do things like clean up oil spills and deal with heavy metals.
Okay, now we're going to go into our actual experiment with all your hopefully good background knowledge now on mushrooms. So this is what we actually did. So this was our research question. Our research question kind of evolved a lot throughout our process until we kind of landed on this one. So based on our findings, can mycelium transport heavy metals? So we wanted to know how far it could transfer it, if it could transfer it in the first place. So from point A to point B, because everything, it's all one organism. And theoretically, we were thinking it should be able to transport heavy metals if it can transport nutrients throughout. So this was our final research question that we landed on. This is the kit that we actually used. So what we did was we ordered a grow kit online. You can just order them online. They're for growing and eating. And so it came in this block of substrate. So that's just the growing medium that mushrooms and fungi will use to eat and grow. And in our case, it was made of wheat bran and hardwood sawdust because this specific mushroom eats wood and so sawdust. Okay, and then this here, this is a model of our block. You're going to be seeing this a lot throughout. And so this is what it actually looked like. There was measurements online, but it was kind of, if I just told you it was like 21 centimeters by 13, you know, it's kind of, it might get lost. So it was about this big. I'm just going to show you with my hands. It was about this big. It wasn't huge. And it was just a pretty solid block of substrate inoculated with the mycelium. So that just means there was already mycelium in it. That's why you see all this white stuff. The brown behind it is the substrate itself. So that's the hardwood sawdust and the wheat bran. And this white part is all the mycelium kind of intertwined within it. And it came wrapped in this plastic bag. So basically what we had to do was cut an X into it. We just followed the instructions on the website and then mist it, which is what we did. So we misted it 3 times per day. Before I did anything, as soon as I cut it open, we took a control substrate. So we just took a chunk out of it right off the bat so we could use that to compare later on. So we just misted it 3 times a day, just with distilled water to actually get the mushrooms to grow. We did that for 8 days. And then finally on day 8, we saw 2 little mushrooms. I would have put a picture here, but they were so small and blended in so well with the actual block that even like my macro lens on my phone could not take a good picture. It wouldn't have been like anything of substance because you couldn't see the mushrooms that I was actually pointing to. But we found 2 within that X. They were extremely small, like I'm talking super tiny. And so these were the mushrooms that we wanted to focus on now that we saw 2. Because we didn't actually know how many we were going to get or if they were even going to grow. So now that we had 2, we kind of had an idea on how to move forward. So what we did from day 10 to 14 is we made a 0.05 molar solution of copper 2 nitrate. And then every day from day 10 to 14, we injected it, 10 milliliters of it, right beside mushroom A. So that's what this blue block is, the blue square. That's the injection site for the copper nitrate solution. So we wanted to really target mushroom A with this. At the same time, we wanted mushroom B to kind of be our control in a sense, because it was away from the injection site for the copper. But we wanted it to have the same amount of like water given to it, so we didn't just like kill this because we overwatered it and then say, oh, it died because we put copper in it. So then we also put 10 milliliters of just water beside mushroom B at the exact same time as this, just to make sure that it was the same amount of liquid going to both. So we just continued to do that. After day 14, that was like time we, day 15 was the day before our experiment was actually completed on the beamline. And so we took our samples. Mushroom A and B is what we were hoping for. But when we actually got into the lab to take our samples and kind of unwrap the block, we found 2 more mushrooms at the top that were actually much more developed. So this is a picture of mushroom D. It was approximately 9 centimeters. I'll show you a picture of mushroom A on the next slide, but just know that they were much more developed. So they're kind of surprise mushrooms for us, but they worked really well in that we had injected the copper way down here. So the ones way up at the top of the block would have been a better kind of control to see if it had transported all the way up to the top of the block.
You're at halftime.
So this is mushroom A. It was about 1 centimeter, really small. It's kind of this weird looking bundle right in there. And this is where I took our substrate samples. So this was a control. I took it right at the beginning. This is substrate A. We called it the contaminated one because all of the copper solution had pooled at the bottom, and this was blue. So we had a pretty good idea that there would be copper present down there. Substrate D was up near that really developed mushroom. We just took it to see what was up there. And then substrate C, we actually like bored into the block, and we got a piece from the middle. Okay, and then here's our actual data. So first, I'm just going to go over the axes. At the bottom, we have the energy level measured in electron volts. And on this side, we have the photon count. In our case, it was normalized. I normalized it. I didn't realize that until a little later, but that's why it goes to 14. Instead of on some other graphs, you might see it go to like 14,000. So I've just normalized it to this highest peak. So the data will not look any different than if I didn't. Yeah, so this is what we actually found. The blue line right here is mushroom A. So that was the one that we injected the copper right beside. It would have been nice to have the block next to the graph, but then the graph would have been unreadable. It would have been too small. And so I'm gonna have like a findings that will have it a little bit clearer. But we did see this really big spike in copper with mushroom A, which is what we expected. It's kind of what we wanted to do. And then along with that, we found manganese, iron, and zinc, also potassium, but the bump was so small on this graph that it actually just kind of hindered the entire thing to have the entire graph rather than zoom in on the actual like seeable peaks, but there was a small potassium peak as well. And then this is just a stacked bar graph showing the exact same thing as the XRF graph, the spectra, just showing that mushroom A definitely has a lot more copper than the other two, or the other three. And then this is the substrate data. We saw the exact same thing. Substrate A, which is that contaminated one that was blue, definitely has a lot more copper in it compared to all the other ones. And again, manganese, iron, and zinc all showed up. In this case as well, substrate D, which is the one that we took next to the super developed mushroom at the top, it actually had more manganese and iron than the others. I'll get to maybe why that is, I think like right on the next slide. So our findings, first and foremost, mushroom A had the highest concentration of copper relative to the other mushroom samples, and substrate A also showed the highest concentration of copper relative to the other substrate samples. Now, so this is a block. So we had the injection point right there, right beside mushroom A, and then it all pooled down to where we took substrate A from. So this really wasn't too big of a surprise to us that we saw the most copper in this, because we that's what we wanted to happen. And again, there's that bar graph, just like reiterating the point. And then we also found zinc, iron, manganese, and a small amount of potassium present in the mushroom and substrate samples. And so we attribute this to the fact that these are just normal minerals found in oyster mushrooms. You'll just find them in any mushroom pretty much that you buy at the store. And so these weren't like out of the ordinary findings. They did show up on our spectra. As well, the substrate samples, because of how the block was, a lot of them were very much intertwined with mycelium. And so that's why we also found it in the substrate, was because the substrate and the mycelium, you could not pull apart. It was very much intertwined. So when we took a chunk, that's the chunk we took. And then finally, copper was found in all mushrooms. This could point to the transportation of copper throughout the mycelium, or it could just be the copper that is naturally present in mushrooms. And so that kind of hindered our entire project. Like realistically, or if we had gone back, we would have had a control mushroom that maybe we got from somewhere else that was about the same size. And so our conclusion, our question was, can mycelium transport heavy metals? The answer to that is, unfortunately, it's inconclusive. However, with the scope of our project and the time we had, I feel comfortable saying that it was inconclusive. We did see copper show up in mushrooms and substrate away from the original injection site, but there is also naturally occurring copper in mushrooms. If we could redo our experiment, we would also test control mushrooms so we could compare the copper content of those versus our mushrooms. And so we could figure out the answer to our question if we had a lot more time and a lot more resources, but we don't. And so this is kind of where our question ends. But I'm fine with that just because of how, kind of short our thing was. So really the answer is we don't know, but we did see copper everywhere. Now hand it up.
Perfect. So why does this matter? We're going to talk about some of the connections, both to inquiry and science, as well as connections we've made to the class and to this learning methodology. So really, the biggest connections that are present here and also present in inquiry are connections with experts. It's an essential part. We don't expect any student to have all the answers at hand or to do all the research alone. When you want answers about a specific topic, you should go to experts. So at CLS here, we have computer scientists, there's physics, biology, chemistry, material science, geology, medicine, all coming together in one place. And that's kind of really the point of inquiry. That interdisciplinary learning really is what inquiry is all about, everyone coming together to guide that learning. During the course, we also got to hear from Little Bear, who talked a lot about how we can benefit, both sides can benefit both Western science and Indigenous ways of knowing. And we'd like to touch on that quickly. So in some ways, they're different. Western science tends to focus on the quantitative data, whereas Indigenous knowledge is more qualitative. We also see that in Western science, it's more about unlocking underlying truths that exist in the world, whereas Indigenous knowledge, it's about symbiosis or the connections between things in the world. Also, Western science is more research-based, where Indigenous knowledge is more about generational considerations. And Western science also emphasizes repeatability, whereas Indigenous knowledge, as Little Bear says, is about how the world is in a constant state of flux. Also, Western science tends to have specializations. Like I mentioned here at CLS, there's a lot of specializations, whereas Indigenous knowledge approaches it from a more holistic point of view. But the things they have in common, as Little Bear pointed out, is that in Western science and quantum physics, it's true that energy is present in all things, both living and non-living. And the interconnectedness and sustainability and how important that is for science to take place, because it is part of a community and a part of our society. Finally, I'll touch on the conclusions and what we learned. So pedagogically, what we took from this was that the strength-based approach is really beneficial, both for us and for our students. Find out what people are good at and allow them to use those skills to guide their learning. Also, learner engagement. Anyone that's been in a classroom knows that having students engage is probably the most difficult part. The beauty of inquiry-based learning is that it's inherently engaging. People are following their interests to wherever they lead. So from that point of view, all of us, we're deeply engaged in this, despite having everything else going on in our lives. Inquiry is also interdisciplinary, as I showed on the last slide. We need to find experts. We need to find diverse perspectives on topics, and that gives us the most holistic and therefore most accurate version or view on a topic. Here are references. Does anyone have any questions? Okay.
Questions still? Because I'll go.
Yeah, please, yeah.
No questions? Okay. What did you find to be the most challenging part of your experiment?
When you say experiment, you mean like the whole
The
process?
whole process, yes.
I would say nailing down one particular topic. It's part of the problem with inquiry too is because it can be so broad, at some point you need to narrow down and actually be coming out with a single message, question, answer. So in that vague, nebulous area of trying to pin it down, I find that the most challenging personally.
Yeah, I think like going off of what Spencer said, at the beginning, like we kind of cycled through a lot of different research questions, what we actually wanted to do. Originally, our project was on the different uptake capabilities of mushrooms. So can it uptake copper better than zinc or better than nickel, and all that. And so it was kind of a back and forth, and it took a while to actually like finally get to a point where we're ready to start the experiment. And so that was really challenging, partially because of like, we have to get this done because we have a time constraint, but also there's just so many things we want to do, and how like, is it feasible to do such a thing? And so I agree with Spencer in that just like nailing down what we actually wanted to do and also could do with the time we had and the resources we had as well.
Quickly, I'll add to almost turning back the engagement. We were so engaged that we're like, oh, we want to do 4 experiments here at once. So really kind of toning that down was tricky.
I want to give you the opportunity to answer if you have something different.
No, I'm good.
Okay. So then the next thing is, as teachers, what is the one thing that you want to make sure that you take into your future classrooms?
I'll start again. To me, I'd say 2 things. One, the benefit of diverse views on things. As a teacher, a lot of the time you want to feel in control of your classroom, of where the learning is going. So relinquishing that control feels quite daunting. But I do feel that if I can let other people into the classroom or let students actually dictate the learning, I think it's a better outcome. Yeah.
Kind of similar, but I like the idea, like through this course, I kind of learned that like I always had the idea that inquiry was like this huge project. Like when I did it in school, it was choose any topic you want and research it. And when I was in school, I found that really daunting because I was like, there's so many different things I could do. And I wanted them to narrow it down, but they never did. But just the realization that it doesn't always have to be that open-ended. We had some readings on the different like levels of inquiry, and like there's ones that are more structured, but still allow students to have the freedom to question things. But maybe in a more like controlled setting, you're kind of guiding them, but they still have the freedom to ask the questions that they want to, but maybe not every single question possible that they want to ask. And so that was really meaningful to me, was just knowing that I can still do inquiry, but not like this huge, big, open-ended one. Because I felt like it was daunting for me. So it's probably, at least I'm hoping I'm not the only one that was like that. So if I felt like that, there's probably some of my students that are feeling like that as well. So
I felt like that. Yeah, that was to me what I was going to say about it's. I had this one idea that inquiry is this big, huge thing, and then through the readings and through our own experience, you can do it to lots of different degrees, and finding that balance through like the constraints. Like Tracy would come up to us and be like, "Hey, is this a good idea?" Like, "Oh, okay, yeah," like those kind of things, and like being that facilitator, like still giving like empowering students to lead their own learning, but facilitating it from the side, being like, "Hey, maybe you should go this way so you don't waste a bunch of your time." Yeah, that's what I got out of it.
I will add my second point here, just that yeah, we really want to guide students, but I guess as you were really saying is that that tightening and widening to kind of guide, be the bumpers, so to speak, of their bowling. Yeah.
Okay. Thank you.
Alrighty. Well, yeah, thanks everyone for coming, and all you at CLS that took the time out of your day to come watch our presentation. So our group focused on heavy metal contents in popular protein powders. My name is Mitch Girolami. I'm a fourth-year education student here at the University of Saskatchewan with a focus on English and physical education.
My name is Peyton Isaac. I'm in my 6th year of schooling. So I did 4 years of kinesiology and now I'm in my 2nd year of education with a focus on physical education and English.
My name's Taylor Wilkinson. I'm in my 4th year of the kinesiology and education program with a major in physical education and a minor in Indigenous studies.
My name's Austin Sloan. I'm in the same boat as Peyton, 6th year in ed student. Get it down.
My name's Brooklyn. I'm in my 4th year of kin ed, physical education, and a minor in social sciences.
All right. So before we kind of dive into our presentation, we just want to do a little bit of a land acknowledgement. We respectfully acknowledge that we are gathered on Treaty 6 territory, the traditional lands of the Cree, Dene, Dakota, Sioux, Saulteaux, and Métis peoples. We recognize the Indigenous peoples who have stewarded these lands for generations. We commit to fostering mutual understanding, respect, and collaboration with Indigenous communities as we work towards reconciliation and a shared future of harmony and equity. So we're going to give you guys a bit of a rundown of what our presentation is going to look like. So just so you guys kind of know the direction we're going to go with it. We're going to start with a brief introduction. So we're going to introduce our research question, why we chose the topic of protein powder, a little bit of background information on protein powder and pemmican. Some of you might be wondering why pemmican. We'll get into that a little bit later in our presentation. And then we'll give a little bit of our group hypothesis before we conducted our research. The second part of our presentation will go into process and procedure. So we'll look at the types of samples, how we prepared those samples, the process of using the XRF scan, and then how to get spectra. We'll then dive into data analysis. So kind of the analysis of our spectra and our XRF results. And then Peyton will explain a little bit of that data. We'll then go into our pedagogy. So the pedagogical practices used and developed because of this class and our research. And then we will go and kind of wrap everything up in our conclusion. So our research question is, how does the heavy metal content in vegan protein powder vary and compare to that found in animal-based whey isolate protein powder? Do metal contents found in these protein powders lead to long-term health complications? So hopefully, based on our presentation, you guys can find that out. So why did we choose protein powders? We tied it back to this idea of personal interest. As you can see, we all come from athletic backgrounds. All of us grew up and some of us still do play competitive sports. And because of that, we have been or are currently taking protein powders. We thought with our consumption as longtime users, this would be kind of an interesting topic to go into to see what we're putting into our bodies, if it's actually good, if it does more harm than good. And so after kind of formulating that research question and reflecting on our backgrounds, we looked into some scholarly sources to kind of help us take a direction on where we wanted to go with our research, kind of help formulate that research question. And what we kind of found is authors such as Bandera looked at specific heavy metals that may be found in protein powder that do have a carcinogenic risk attached to them. And then we also have authors such as Ring and Elgamel that used plasma spectrometry to test protein powders to look at if there are long-term health effects linked to long-term and excessive consumption of protein powder.
So we'll start off, what is protein? Protein is one of the big 3 macronutrients. You have carbohydrates, fats, proteins. They're composed of amino acids, and those can be broken down into essential and non-essential. We have 9 essential amino acids that our body cannot synthesize on our own. That requires us to get them from the diet. The role of protein in the body, majority of the chemical reactions in the body are catalyzed by proteins. They regulate the immune system, they control gene expression, and they form the majority of muscle. So some guidelines. There's a lot of recent research on potential guidelines for protein intake. The newer research suggests a little higher of a guideline at about 1.6 grams, 2 grams per kilo body weight favors good muscle adaptations. So a little bit about protein powders. What are they? They're concentrated forms of protein. We're going to run into a couple types here in our research. We chose to look at some animal-based, which will be mostly whey, and some plant-based, which all contain pea, rice, soy, hemp proteins. They're all in blends. The processing we'll get into in the next couple slides. They're different, but they're also kind of similar. Next, please. So processing whey. Step 1, pasteurization of the milk. This is simply just heat treatment to get rid of some of the microorganisms that we don't want to ingest. Step 2 is the separation of the whey. As you can see here, this person is making homemade cheese. This solids is the curd. This whitish looking liquid is the whey. Next, we have our filtering. So we're going to remove the lactose, the fat, the water, the minerals. We get into microfiltering. This is, again, just taking some of the stuff we don't want. Microfiltering turns what you have into a protein concentrate. So that's anything above an 80% protein content. The next step is ultrafiltering, which then again takes that step and goes a little further. That's anything with about 90+% protein content. And step 6 is drying. They usually put it into like a spray gun, spray it on these cooling racks where it cools and becomes a powder. So for processing vegan, step 1 is the cleaning and prep. So it's like deshelling, washing, rinsing, getting it ready for the milling process. Milling is just grinding up ingredients. And step 3 is filtering again. So they're using a bunch of different techniques to get what they don't want, or to get what they don't want out of it and increase the protein yields. So the isolate and the concentrate still apply here, 90+% for an isolate, 80+% for a concentrate. So why would we use them? They offer a high protein to calorie ratio for lots of people in sports, nutrition backgrounds. It's kind of tough to get your protein intake in sometimes, especially when you're having a busy day. So protein powders offer usually about 30 grams per serving of protein. It's convenient, relatively cost effective. Chicken's about $1.65 for 30 grams of protein, and lots of powders are about $1.55 for 30 grams of protein, or a little bit less. So they're very cost reasonable. They're versatile. You can add them to lots of different foods or baking. They're easy to pack around, and they're dry. So as long as you don't pre-mix them, you can take them wherever and they last a very long time. So that brings us into the original protein powder, pemmican. What is it? Usually dried meat, traditionally bison meat. However, the indigenous peoples would use whatever meat they could get their hands on. So moose, elk, deer, antelope. It's pounded into a coarse powder, usually with a rock, combined with tallow, which is just rendered fat, and typically mixed with berries. So it's cultural and historical use. It's a high protein, high energy food that can easily be preserved for winter months. The fat being rendered is a key factor, so it doesn't go rancid. Again, we're just cooking the fat, getting all the impurities we don't want out of it, so it lasts way longer. That's a traditional indigenous farm protein supplement. And that's pretty much why we chose to analyze it, especially in like a direct head-to-head against our whey, animal-based against animal-based, just see what the results were.
All right, so based on everything that Austin kind of just broke down for you guys and those scholarly articles that we dug into, our hypothesis going into our research was that air, soil, and water pollution in certain growing areas could lead to an increase in heavy metals and other particulates in plant-based protein powders compared to animal-based. These heavy metals may lead to long-term health effects for users. And I'll throw it over to Brooke, who's going to run through our process and procedure.
Okay, so our process and procedure. So here's an overview of our samples. We had 2 brands of whey and 2 brands of vegan, as well as our pemmican. So both brands, brand 1 and brand 2 of whey, had like the same consistency. They were very fine, very dry. and very light. Whereas the vegan was a little bit more like clumpy and chalky. The pemmican came like in a pemmican piece, so it wasn't like we hand grinded it to kind of break it down to try to get it as close to the same consistency as we could for our whey and vegan powders. However, it was very hard to get it that fine. So this, the different characteristics of these could have a little bit of an impact on our data. So our sample preparation, this took place in a dry and sanitized environment. We were given handy dandy kits from Tracy, which allowed us to do this sample preparation. We made sure to use gloves and clean our slides to limit any contamination. And using the Beamline. So this was something all of us were feeling very nervous for. Our friend Peyton here left us to go to Peru. So the four of us had to take the hands on this one, but Tracy had taken us through all the safety considerations while using the Beamline, and we also participated in some online safety training modules, which were very handy. One thing about using the Beamline was this was all new to us. We were very excited, but yet very nervous. Me and Taylor let the boys go first on deck here and kind of watch them and made sure we let them figure out the kinks before we went so we didn't look silly. But yeah, so this was a large part of our inquiry-based learning and an experience that we were very grateful for.
All right, so before we let Peyton break down our spectra and our results, we're going to go into a little bit about XRF and how do we actually get spectra. So here we're going to show you guys just a quick little video. I'll be honest, this guy explains it a lot better than I can. So it's about 45 seconds here and we'll let you hear what he has to say.
There's sound. We're radiating a sample material with X-rays from an X-ray source. Every material is made up of many atoms, and each atom has a positively charged nucleus surrounded by a cloud of negatively charged electrons. The electrons orbit the nucleus on distinct energy levels or shells. When X-rays encounter an atom, they're absorbed by the electrons orbiting the nucleus. If the energy from an incoming X-ray is high enough, the electron receiving the X-ray will be released from the atom. An empty electron spot close to the nucleus is not a stable state for an atom, so it will pull an electron from a farther away shell to fill that spot. When this happens, a new X-ray is emitted as an X-ray fluorescence photon, which is unique for each element. The energy shells from an atom are named alphabetically.
All right, that was a little brief tidbit.
An XRF experiment begins by...
There we go, perfect. All right, so now I'm gonna try and explain it. We'll see how I do here. So this is just kind of a test sample. And so what this spectra is showing is it is showing the results of a tissue that was wiped on a copper pipe. And so obviously at about 8,000 on the x-axis, we see this big peak. That is our copper. And so essentially what happened is as that X-ray or those X-ray waves were going through the sample, they would have essentially charged up an electron on the K shell of a copper atom, displaced that electron that then needed to be filled because as the video said, if it doesn't have an inner electron in the inner shell or it gets displaced, that's unstable. So as we'll say, maybe it comes from the L shell, the electron moves to the K shell, it gives off energy, which is then picked up by the photon collector. That one took me a while. The photon collector. And then that is what is being graphed on this spectra. Killed it, eh?
Yeah, you can. Okay, so now I'm gonna go over kind of our spectras. So like my group said, I wasn't actually able to be here for the day of the Beamline, so I kind of took it upon myself to look at the data and what they did, just so I felt like I wasn't falling behind. Okay, so we have brand 1 and brand 2, and in brand 1 and brand 2, we have a vegan and a whey. So we started by taking 2 samples of each. So we had 8 samples to begin with, and that was just for our own confidence in our sample prep and how we were using the Beamline to just make sure that we were being consistent throughout. So as you can see up here, this is just brand 2 whey, and it was tested twice, and then here brand 1 vegan, and we did this with all of the samples. So then at the end of the day, we said, okay, we don't actually need to look at all 8 samples. We can see that these are pretty relative. We can see that these are pretty relative, and same with the other ones. So we're just going to take 4 of the samples. So just 1 from everyone. Another thing with our spectras is the peaks represent a relative concentration of the heavy metals, not an absolute, because like Brooke said, some of our protein powders had different consistencies. And then our group, we decided to make an educational hypothesis, and we know that the XRF graph doesn't actually tell us how much of the protein is in it, but based on like what we know about the protein powders, we correlated a higher peak with more of that element being present. Okay, so this first spectra, we have brand 2 and brand 1, both of the wheys being compared, and then we have brand 1 and brand 2, both of the vegans. So we can see between the 2 brands, they're pretty similar in their heavy metal concentration. Nice. Okay, so this next spectra shows brand 1 vegan and whey being compared, and this one shows brand 2 vegan and whey being compared. So this one gives us a better idea. We can see that there's more iron, manganese, copper, and zinc in our vegan protein powders when compared to our whey. And then we can see that there's greater levels of calcium in our whey when compared to our vegan. Lastly, this last spectra again just is graphed all of them together. So again, we can see that there's more levels of manganese, iron, copper, and zinc in our vegan, and more calcium in our whey. So the greater levels of calcium is because our wheys are produced of like milk and soy. So those are going to have higher concentrations than our vegan ones. And then the greater levels of copper, manganese, zinc, and iron is because our vegan protein powders come from plants and soil that naturally contain higher concentrations of these elements. So it makes sense why they would show higher concentrations of. And then as Austin talked about, we looked at pemmican and how it compared to our like natural or our whey protein powders. So one thing here, you can see that pemmican has more zinc and bromine. Zinc makes sense because there's more zinc in meat sources than there would be in like milk and soy. The bromine one kind of threw us for a loop. So one thing that I found is bromine is used as sanitation. So some farmers use it for their crops as a fire retardant. So what could have happened is it could have been like leaked out of it and then into the soil and the plants where then the berries from the pemmican came from. Another thing was when we were preparing our samples, there could have been bromine like just in our kitchen that we were, and like the utensils that we were using to turn the pemmican into the protein powder. So then just kind of to go over our findings, there was no unexpected metals, so it's okay, keep drinking your protein powders. There's very minor differences between whey and vegan, same with pemmican and our protein whey. Based on these findings, we can conclude that there is no correlation between whey and vegan protein powders or long-term health effects. So they're safe.
And now that we've concluded our scientific portion of our research project, we'll go into the pedagogy. So we focus on 3 pedagogical practices from our 411 experience, and that was collaborating with topics of interest rather than people, student approach, and reflection and analysis. So collaborating with topics of interest rather than people, we found a value in collaborating with people that we had common interests with rather than our best friends. We also found that because we had common interests, we also shared similar values of communication, expectations, adapting. We've all been student athletes or athletes on teams, and when working with teams, you share similar qualities of group work. And then using outside people as resources to enhance knowledge. Because we're all athletes and a few of us are student athletes, we have team nutritionists who we could reach out to and discuss our protein powders with, and then also athletes that knew supplement people and things like that. And then student-centered approach. So the 411 research project allowed for a shift in approach from teacher-led to student-led learning. which allows for students to take ownership of their learning and allows for increased engagement, which we found using the Beamline. I know I learned a lot more being hands-on than I would have just sitting in a lecture, and I think the rest of us would agree with that. And then it allows for students to take their own approach in order to gather evidence, conduct research, and analyze data. So for us, we really got to personalize each group got to personalize the way they approached their project. For us, could have been different than another group. And then reflection and analysis. So Mitch, do you want to press again? The picture might show up. There we go. The inquiry-based approach allows for reflection through a multi-step process. So we start with asking, and then we go into investigating, creating, discussing, and reflecting. And this is a continuous circle where we allow our students or ourselves to ask and then investigate. And as we get to reflect, that just creates a deeper understanding of your topic through discussions and reflection. For us, we got to take a lot of opportunities in class to discuss with other groups, get feedback from other groups, continue to reflect as a group through Zoom calls, multiple class discussions, and change our project to continue to dive deeper into it. And then we can integrate this into the classroom. So for all of us, we plan to be future physical education teachers. And so we know that we'll use group selection quite often, and we can utilize different group selection tools. So we can use the collaborating with common interests. We can also do random group selection, which also shows benefits. When you have people who have different interests, sometimes they hold different knowledge or different skills for gym class that you can utilize, and you can help each other out. So there's different ways that you can do group selection with both having benefits. And then student-centered learning. In a phys ed class, you can have students create the games. They can lead their peers through warm-ups, through games, have their peers asking them questions. It just creates a deeper learning experience. And then inquiry-based learning experiences. So in a phys ed class, you can start your class with an essential question. So really diving into the why of games, understanding when you use a skill. So teaching games for understanding. Why do you use this skill? When do you use it in a game-like situation? It just allows for students to dive deeper. And then we'll go into our final conclusion here. So we took away in our 411 inquiry project that incorporating practices that allow students to take control of their learning enables students to question, reflect, and develop a deeper understanding of content that creates lifelong learners. Our references. Thank you for watching.
Any questions?
Oh, come on, I can't be the only.
Alright, yeah. I like this crowd.
We nailed it, I guess. I don't know.
Oh, Tracy goes.
I have a question. Yeah. Just to break the mold. So I really liked how you talked about how, you guys are obviously not a science background. You're more interested in like application and such to something that you're interested in, which from my understanding is ed and whatnot. And so I think could maybe each of you comment a little bit more about how diving into like from a scientific perspective can be applied to your actual interests in the classroom. And I think you kind of had that on a slide just about like how you're going to take this into an education setting where you're like gym teachers and whatnot, but maybe just like how diving into different atmosphere, like from using the synchrotron or using a scientific project can be applied to like other sort of areas of interest.
Yeah, I can talk about that. So for example, using the synchrotron and learning that software, Tracy kind of just sat back and was like giving us guidelines a little bit. They were a little loose. So like she always said, it was a lot of trial and error. And I think that's a skill that can translate to a lot of different areas of education and schooling. And for me personally, as a future educator, I like to use that trial and error, kind of figure it out on yourself. Learning how to throw a ball, just try to do it for 5 minutes. See how you do it, not necessarily me going over the basic steps, the learning cues right off the bat, a little bit of exploratory learning.
I can also add one thing quick. I went to a sports academy in high school. Probably definitely a place that if you were very keen on your education, you probably wouldn't have necessarily wanted to go to. So when I found that we were taking a science class, I was like, I can't take this class. Like, I don't even know when the last time was I like actually like understood science. I was sitting in the first class and I texted Taylor, I'm like, I can't take this class. Like I feel dumb. Like I don't even know what any of these words are. Like everyone's really, really, really smart in this class. Like this is not up my alley. And I just like want to say getting my feet wet and like just like jumping in and being like, okay, you know what, we're gonna try it. And if it doesn't work, like we'll figure it out. And helped like all of our classmates and Tracy, obviously, and my group members, but definitely go for it. And I think that's like a large takeaway from this class is like this might not definitely wasn't something I like thought I was gonna find myself looking at all semester and being totally fully engaged in by probably like the third week of class. So that was a large takeaway for me.
Yeah, I'd agree with Brooke, just like being comfortable with being uncomfortable. Like, I know even leading up to the Beamline, I was like, oh my gosh, I'm not gonna be here for the Beamline, like, I'm screwed, I'm not gonna know anything. But then once I actually started looking at the data, I had this like giant light bulb moment where I was like, oh my gosh, I actually get it. Like, I get what's going on now, and I didn't feel like I was just in the blur. So I feel like when you take that into a gym class or any other class, you have resources around you, whether it be your students, your coworkers, where if you don't know something, it's okay. But I think just your effort to try and know something goes a long way.
Love it. That's so cool.
So you might anticipate, what was the biggest barrier that you came across? How did you overcome it?
Science.
Honestly, like,
I think
So I would say the barrier wasn't the science, the barrier was your fear of the
that's
science.
exactly what I was just about to say. I think the biggest thing for us was the uncertainty and that unknown fear, because as you heard, I don't think any of us said we have a background. So when we got into this, and like Brooke says, it was very intimidating at the start, but I think that's the part of being a learner. And then as future teachers bringing that into our classroom, right? Like we were very uncertain, very unsure, very nervous, but we had a great class and a great teacher, and everyone was very supportive and wasn't afraid to give constructive criticism when we needed it, right? And so that whole process, it wasn't so much the science, it was how we get over that fear of that scary word science to indulge in our learning and become those lifelong learners. That's what I would say.
Yeah, I also want to say I've had a very comfortable experience through university the past 4 years. I started on Zoom calls, very comfortable. Had teammates in all my classes after that. Classes where I could just sit at the back of the room and not talk. So being forced to do this, I did want to get out. Sorry, Tracy, I did try to get out. But I'm glad I didn't, because this is really going to help going into the real world of feeling uncomfortable and developing ways to get through that. Also had a great group, thanks guys. But I really think that this has probably been the biggest takeaway from my 4 years. So that's awesome.
we have more questions.
Oh, no.
Wow. Oh wow. Whoever wants to go first, just let's dive into it.
So mine is just more so of a comment.
Okay, perfect.
How you guys were talking about you don't have a science background and are more in English and present or kinesiology and stuff. Just want to remind you that kinesiology is
Right.
Touche.
you be confident in that because you are doing science. It's just a different.
For sure, yeah.
Dallas.
I would have to disagree with that. No, I have a question, just personal preference. I'm curious, just for your group, what preference do you have as either vegan or non-vegan protein? And would you ever skip the protein and chew on some pemmican?
I'll start. I love whey. I'm a whey girl. I tried vegan once, not a vegan girl. I'm a whey girl. Pemmican, we didn't like it. Yeah.
I didn't mind it.
However,
I didn't like. I don't like it, though.
I love wild meat. Like I would way sooner eat for my elk and meat moose in my freezer than I would my ground beef. I love elk jerky, so I don't know, it wasn't like it was like, oh, like this is bison meat or anything like that. I love my wild meat, but I don't know. Yeah, I'm definitely a whey girl.
Dallas, whey, the only thing that whey has on vegan is more like a more complete protein profile. So when you're talking about those essential amino acids, there's more essentials in whey, just because it is animal based. And so usually if you are taking vegan, lots of times you'll get proper amounts of the aminos, but sometimes you might be missing something, so you might have to supplement with another thing to make up for that.
I think the one nice thing too, I didn't try the pemmican, but it would be nice, like if you're on the go. So like I know like protein powders, like we have to like make, or some people like pre-make them before they're going or after, but like something like pemmican would just be an easy way to get protein in your body quicker. So I think that's where maybe I would use it if I liked it.
Put it bluntly, 100%, I'd nibble on some pemmican. I thought it was cool for us too, because before going into this, I really didn't have a lot of knowledge on pemmican, and that's where it was awesome. Thank you, Dallas, for kind of introducing us to the idea of pemmican and being that original kind of protein supplement. And then also gave us an opportunity to reflect on how we can bring Indigenous content into a science discussion, right? So I guess also I don't know what an air quotes here, but yeah, sorry, science. But yeah, to answer the question, I tried it. It's like beef jerky in my opinion. So I would nibble on some pemmican.
Mine were the vegan sources, and these guys told me it smells. So mine were the vegan sources that we used.
It smells like wood.
It does smell like wood a little. Tastes better than it smells.
I wonder if it would make a good substrate.
No wonder.
Let's collab.
I was just gonna say. Next year, I'm not gonna.
Come out here by next year.
Okay.
We got one more thing.
Okay, which brands did you end up testing?
We can't tell you that. Secret, but I'll tell you later. I can't tell you on Zoom.
Might be a spy, I don't know.
They might be watching. Might have a lot of YouTube viewers.
Hello, everybody. Hi. So we are all education students, and we wanted to talk about heavy metals in pet food. So my name's Sharissa. I'm in the early year stream, and my major is science, and my minor is social studies. Oh, I'm Monique, and I major in science and social science, and I am in my second year, kind of, but it's kind of weird because I have an international degree background, so I'm just doing courses all over that is that I need, so it's kind of weird, so I don't know where I am.
I'm Jessica. I am considered a second year student, but I've been perfecting my teaching style for 8 years now, which is crazy. And I study English and science.
I'm Mariah. This is I'm a third year education student. This is my 7th or 8th year on campus. I have a prior BA. I got my first degree in history, so my teaching areas are social studies and English. And I'm in middle year student. I do a bit of a music background, so I know no science at all.
I'm also in the same boat. I'm Mara. I'm technically 4th year, also been in school for other things. And my areas are social sciences and English.
Sorry.
Yeah.
Should be.
If you use the space bar, that should also make it go. That is not making it go.
You have to maybe click on the presentation. Like, are we not putting it?
Oh, there we go. Okay, so we're gonna start off with our land acknowledgement. So we acknowledge that we live and learn on Treaty 6 territory, the traditional lands of the Cree, Dakota, Dene, Dakota Sioux, Saulteaux, as well as the homeland of the Métis Nation. We acknowledge the deep and enduring connection of Indigenous peoples to this land, and we pay our respects to the elders past and present who have cared for it. We commit to learning and working with Indigenous communities towards reconciliation, respect, and understanding to uphold the spirit and intent of Treaty 6. We are all treaty people.
So when we started this class, I'm just gonna take this and see if it works eventually. We started out by brainstorming different project ideas, and as you can see from the picture,
many of us in this group are, well, all of us except Monique, but she says she has kids, we're pet owners. So something that's always in the forefront of our mind is the quality of food we're feeding our pets and if it's the best possible option for them. And we had kind of heard just from conversations and online that there's not a lot of regulation in the pet food industry. So we threw that as an idea, did some research. We ended up finding 5 studies just between 2018 and 2023 that focused on American dog food, and it found toxic heavy metals like mercury, arsenic, and lead in pet food at unsafe levels for consumption. We also found that pet food is not regulated by Health Canada. There is a veterinary board that oversees nutritional information, but not the production. So we decided that this class would be a great opportunity to explore the pet food in a Canadian context and look at Canadian pet food and to see if it followed what these studies found. Okay, it works out. So our hypothesis based on the amount of studies we found was that the pet food would contain toxic heavy metals, particularly arsenic, mercury, and lead. And then we looked at a fish-based food. So at the least, we expect to see mercury in that, just from a general knowledge of there being quite a lot of mercury in fish. So we purchased 3 different brands of dog food from just local pet stores. They're made in Alberta, Ontario, and British Columbia. And then we did 3 different types of proteins from each food. This was just to see if the heavy metals were different in different proteins. For example, if there's lots in the fish, maybe there's not mercury in the ham, maybe there's more arsenic in that based on their diet and environment. And then we also used one control just to give us an idea of comparison and have confidence in our results. So we used from our brand A vegetarian food, and then we labeled our brands brand A, brand B, and brand C. Because the XRF can only detect mercury at quite high levels, we also found some heavy metal water test strips that are used to detect lead, iron, copper, and mercury at low levels. So we ground each brand and protein type with combined it with distilled water and used these test strips as one way that we did our testing. And then of course we used the XRF on the Ideas Beamline. So we also ground the dog food, packed it in. We did 2 samples for each brand and protein type to have confidence in our results, and then to pass it on how the Beamline works to Maria.
Oops, there we go. This should be interesting.
Do you want me to hold this one?
Yeah, also my right arm is just for show. It doesn't do a whole lot of anything. It like does that. That's kind of it. Anyway, on that little note, so I'm gonna talk a little bit about how the Beamline works. So we use the Ideas Beamline for our experiment. The Ideas Beamline is the Industry Development, Education, Applications, and Students Beamline. So it's the Beamline that us non-scientists, education students can play with on occasion when you let us. And hope we don't break it. That was a concern for a minute. I was actually worried. I went home and I said, I hope I don't break the synchrotron, that'd be really bad. Anyway, so the X-ray beam is initially fired from an electron gun in a booster ring. And the electrons then get kind of sped up to the speed of light using microwave energy that's stored in the storage ring. The beam is then sent by magnets within the storage ring, which creates the beamline that we use. And then the X-ray beam comes out this part over here. We didn't have a fantastic photo of it, so it comes out over here. And then we put our samples right there. And then the X-rays will interact with the samples through the X-ray. The X-ray beams will interact with the elements in the samples that are held there. And then what happens is that the X-ray beams will interact, and then it will actually like set off a beam of light as well. It's kind of like when there's water in the air and then like sun rays hit it and get a rainbow and this light scatters. It's the same kind of effect. And as the X-rays scatter when it interacts with the elements in the samples, it gets picked up by this detector right here. Next slide. Yes, please. Thank you. So the XRF line is what we use, can pick up the red and pink elements up there. The reddish pink elements are slightly lighter elements than the blue elements. Both can be picked up by the Ideas Beamline, but it's easier to pick up the red ones. So. Yes. So there's a couple different options when you use the ideas line. There's the XRF and the Zanes line. The XRF line will just tell you what's in a sample. The Zanes line will tell you, like, give more specific information about specific elements. Okay, thank you. Anyway, so there's different, each of the elements get picked up at different ranges. And these are all the different ranges that they get picked up at. These and the different ranges are like the amount of energy that gets released. And when the X-ray beams interact with it. And so, yeah, and all these ones are most likely to get picked up because they are the lighter elements.
Great. So first and foremost with our findings, the XRF and the heavy metal test strips found no evidence of the toxic heavy metals, mercury, arsenic, or lead. You can kind of see in this picture, sorry, Mariah, all the light colors here fall within the 0 safe range, and that was consistent across all brands and all protein types that we tested, which is great for the dogs, not so great for us in this class because we weren't really sure what we were going to do for the rest of the semester. But as one of our classmates pointed out, not getting the results we wanted doesn't mean no results at all. So during our beam time, we ran each sample for 1 minute. And right away on the first sample, the zinc peak instantly shot up. We didn't realize it was zinc. We thought maybe it would be iron. But then we looked at the energy table and figured out it was zinc. And this started happening across all the samples. And as you can see, iron's our next highest, and then calcium, and they're like quite a bit lower than the zinc. So we were wondering what's going on with all that. Is zinc good for dogs? Do they need it? Is too much too bad? And why was there so much in our samples? Some of our samples were grain-free and some of them contained grain. So as we went through beam time, we thought maybe that was the difference, but that didn't appear to be. So we did leave beam time knowing that that was where we were going to go, start exploring the zinc.
Oh. So my science is very limited when it comes to, the body and if zinc is good. So the peak instantly sparked my curiosity. I was like, okay, well, what is zinc? It's, it's a trace mineral, meaning the body doesn't really need a lot. And well, what benefits does it give to dogs? It, it provides like enzymes, proteins, and hormones, and then it benefits their immune system, their skin and coat, make your puppy pretty. And I'm like, okay, well, is it harmful to dogs? And it was really hard because we couldn't translate the numbers. So I was like, okay, it's saying, it could cause low red blood cells, vomiting, diarrhea, depression, and lack of appetite if there's too much in the food. I'm like, okay, well, how am I going to do this? I'm going to treat it as if I'm grading something. And I was like, okay, so I'm going to take the entire list of ingredients, find out which ones have natural zinc in them, and then just grade them. And it was like a lot. I mean, 42% of the ingredients containing zinc in just one little kibble. That's pretty high, especially if you're like me and you like to spoil your baby. So then I was like, okay, well, what's with the low one? It's still high, but it's not as high. And I looked at all the ingredients again and realized, our highest one, which was brand A fish, had 17 total vegetables and fruits. And I'm like, okay, and what about our lowest one? Well, our lowest one only had one. I'm like, oh, interesting. So that was really fun to dig into.
Sorry.
Yeah, so on top of the ingredient analysis, we did some background research. And so like Jessica said, dogs do require zinc in their diet. It was hard to find an exact dosage, but the most recent one we could find was 60 milligrams per kilogram of dry dog food. Zinc poisoning can happen, but the only information we could find was that it has to be in really high doses
which usually is from something non-edible, like sunscreen, diaper cream, jewelry, nuts and bolts. Nothing we could find suggested anything that's edible to dogs will lead to zinc poisoning. And then we also found a really interesting study that looked at the blood levels of zinc in healthy adult dogs. And they used dogs that were fed dry dog food and dogs that were fed raw dog food. There's no difference between them. So based on this and our ingredient analysis, we found basically that the zinc is safe. So it was interesting to think about because some of us have a little bit of science, but most of us don't. So when we look at our spectra, we were looking at the zinc going up, like I said, and we were all like, oh my gosh, that's so high. What's going on? Why is there so much zinc? But when we look at the mystery sample we did, which our protein group talked about, each group that did XRF ran a mystery sample and this copper peak came up. And so we were trying to figure out, oh, what has so much copper in it? And then we found out it was a wipe that had just been rubbed on a copper pipe. It wasn't necessarily something that contained copper. So this just was a good reminder to think about that the XRF, first of all, it's so sensitive. And second of all, it's just looking at what there's more of than other things. So there's just more zinc than other elements in ours, not necessarily a ton of zinc.
All right, so we're going to talk a little bit about our experience with inquiry. So at the beginning of this semester, I remember sitting in the first class and thinking, there is no way I can do this. This is impossible. I am terrified of using the synchrotron. And I was going through the registration channel looking for any other 411 class that was open. Unfortunately, there was only educational administration open, and that seemed more boring. So I decided to just stick with it, and it's gonna be fine. But so a couple of us were quite intimidated about the idea of using the synchrotron. It's the only one in Canada. It's super expensive. It just, why are you trusting me to use it, you know? So once we finally got settled within our group and started to devise our plan, what we're going to do, what we're kind of looking at, and getting that project kind of put together, it kind of started to feel a little bit more comfortable. It's like, okay, this seems like I can do it. Thankfully, we had an amazing instructor, Tracy, who scaffolded our learning. She provided us support from the very beginning. She encouraged us, and she supported all of our ideas that we threw at her, which some of them were quite crazy. She helped us refine what we were looking for and how the beamline would be able to pick up what we're looking for. And she gave us a lot of guidance on how the synchrotron actually worked and how we can use it to support our project. Tracy showed us how we could create a project such as this one and translate it into actually using it in our classroom with whatever age range of students that we have. So I want to talk a little bit about the different forms of inquiry and the different benefits. So there's many different forms of inquiry, and as education students, we often hear the word inquiry thrown around a lot. We know what the benefits are and how to kind of use it, but we've never actually had a class dedicated to inquiry. And we didn't really understand how we could truly support students through the inquiry project because we've never been taught that. So that was a nice thing to learn through this class. So Tracy helped us understand what inquiry truly is and the multiple forms that we can use in our classroom. So first I want to start off at the bottom of our building blocks. So this is kind of like the first foundational step of inquiry. So confirmation inquiry. In confirmation inquiry, students are provided with questions and procedures or methods where the results are already known in advance and the confirmation of the results is the object. So you just want to confirm the findings. The goal or expected product for using confirmation inquiry is to build investigation and critical thinking skills and learning how different methods of scientific procedures work. And then as we move up, we got structured inquiry, which helps students learn how to ask questions and investigate real world problems. Students are given a problem to investigate and are taught how to use the scientific process to find the solution. The goal of structured inquiry is to encourage critical thinking and give students the responsibility for their own learning, and it helps them develop social skills as well. It focuses on understanding the why and how rather than just the what of knowledge. And we move up again to guided inquiry, where students are investigating a teacher presented question and the students are able to create their own procedure or methods to finding the answer to said question. The goal of structured inquiry is to encourage critical thinking and creative thinking. Guided inquiry also allows for student agency and allow them to be in charge of their learning and the learning process. And then open inquiry, which is what we did. It's quite a daunting task, but it is doable. So open inquiry, students are investigating their own questions and they formulate their own research process. Open inquiry helps students develop critical thinking skills as they're engaging in questioning and designing different experimental arrays and reflecting critically on their findings. It helps them develop problem solving by actively participating in the inquiry process. They learn how to address complex problems. Autonomy, unlike structured inquiry, open inquiry allows students to determine the purpose of investigation and formulate their own questions. And research skills. Students learn how to collect, analyze, interpret data, and find existing information. And lastly, ownership and responsibility. The people who are engaging in the inquiry process take ownership of their investigation, similar to how scientists work. So each form of inquiry has its purpose and how it's designed to support students' learning and can be developmentally appropriate for students of all ages. So depending on what grade you're in or teaching, you can use different forms of inquiry to support their learning.
Engagement. So all these research that we did, we can all say that all the groups were engaged. Engagement is a big topic when it comes to pedagogy. Engagement, students can be achieved in all subjects by integrating your own ideas. If you realize, or throughout this semester, we were given the opportunity to choose what we wanted to do, to form our own groups, and we did it based on our own interests. And because of this, we were more engaged into what we were doing. We all put out for 100%. Like, most of us in here are not scientists, are not from a science background. I was from a science background, but I was more engaged in this project just because we wanted to do it. Like, I started out in another group. Some of you guys know the beekeeping. Yeah, I was a beekeeper back home. Well, I used to raise chicken, goats, all of them. So I know engaging can be quite connected. Engaging also foster critical thinking, deeper understanding, and it gives students voices. Like, this is us using our voices here. Like, because we were so engaged in the project, we carried out the experiment, and we know that there is no heavy metal in dog food, so we can talk about it. And we had to do research. We got more confident in the idea, and we're not talking, so there's none, because we didn't do the research, we did it, and we know that there is none, at least in the brands that we studied. And when students are engaged, learning takes place. We are here, we have learned, like, we all learn what we did in our group. Like, we carried out the experiment, we all learned. Like, you guys learned about our experiment, we're learning about our groups, different groups experiments. So learning is taking place, it's not wasted. We are learning something. So that's what engagement can do. It can make learning happen.
So I'm going to talk a little bit about science application outside the classroom. When students have a chance to kind of do these different types of experiments and kind of get out of the classroom and kind of apply what they've learned, they have the opportunity to figure out how science can translate into real world situations. I think a lot of us, at least those of us who with a love of science, can probably remember sitting in like high school chemistry and thinking, when am I ever going to need to know where, zinc or copper is, other than in pennies or something? But this actually allows students to see, oh, this actually does have an application. There's these chemicals are in like my pet food, or in my honey, or in my protein powder, and all these different things that we use on a day-to-day basis. And it really kind of allows them to understand why science knowledge is important. And as you go through these kind of experiments, it also provides them with an opportunity to kind of develop their critical thinking skills and their problem solving skills if you're going through it, developing a question, testing a hypothesis, doing these different things, which are all very important even outside of the science environment. Another thing that I wanted to talk about was if you have students in your class who are maybe very interested in STEM, which is science, technology, engineering, and mathematics, they may not have an idea of what kind of career opportunities or different things are available to them outside of maybe some very traditional doctors or maybe just standard engineering. And so if you come to a place like this and show your students, at least if they're in high school, like, oh yeah, we took a tour of the synchrotron, we ran into a whole bunch of physicists and engineers and all these different things doing this specific work, and they work with all these different companies and doing all these different types of experiments. It kind of gives them an opportunity to see what's available after, like what they might want to pursue after high school and after university. So just in conclusion, I think what we've learned is in terms of our dog food, there's no toxic heavy metals in there. There's quite a bit of zinc, but zinc, as far as we can tell, is very healthy for dogs, other than if they accidentally eat your hand cream or your jewelry or something. And in terms of kind of translating this to the classroom, one thing that I learned was it allowed me to think a little bit about how to get students engaged in kind of science and have these like real life applications of it, other than dissecting a frog or some of these various different things.
Thank you. Okay. And here's our references if you want. But I'm gonna go back to this slide because it looks nicer.
I have a very basic question, because you were talking about all the different metals at the beginning, and you said something about arsenic. Is arsenic a metal, or is it something else?
I think it's.
Do you know?
It's classified as a toxic metal.
Okay, cool. I didn't know that. I just thought you gave it to like mice or something. I don't know. Thank you.
Thanks for trying to trick us. I was questioning that for a minute. I'm like, is it? Yes, it is. In all our research, it is.
That's great.
Anyone else have questions?
Yes.
Oh, no.
Oh, no.
So you focused a lot at the beginning on the presence of toxic heavy metals. In fact, your reaction to seeing zinc was, well, let's think about maybe that's toxic as well. The fact that zinc is the most common metal you saw is probably not an accident. Dog food is not grouped together. Did you look into what are the symptoms of zinc deficiency?
We did a little bit. There wasn't a ton. Most of the stuff we could find focused more on zinc poisoning, but we did look at like that they do need it in their diet. It's not something they naturally produce, and that there is deficiencies. Jessica mentioned some of it. I think like it affects their coat, and I think
Immune system is a big one.
Yeah.
Yeah. And thyroid function, system function, or yeah.
All the good general
Follow-up question. Did you get ethics approval for that animal you're carrying?
It's not real.
I thought it was real for about 30 seconds. Well, did the tail move on its own?
No, haven't figured that one out. Gotta work on a mechanic for that.
Yes. Hi, Tracy.
Hi. Not surprising. I'm curious what the biggest barrier that each of you faced that you felt, and then how you overcame it.
Well, I can start. Sorry. My biggest barrier was really just coming to the conclusion that I actually am capable of doing this type of science. Like I know some other people said, like we sat in that classroom and I felt dumb. Like, and I had never had a class that made me feel like that. And just my own personal, like I didn't feel confident in my abilities or like my knowledge. I didn't feel confident in it. And so just getting over that like mindset barrier that I can't do this was really tough in the beginning. But then once I got over it, it went really well. And I am actually capable of doing science, which is awesome.
So my biggest barrier, I think, would be myself.
You had a whole kid.
Well, I forgot that part. Because it's like 2 months now, I forgot that part. It's a good part though. Well, it's my personality, I'm kind of shy and reserved. It takes me a while to warm up to things. Like, there are lots of things out there that I know I can do, that I'm willing to do, but I'm always sitting in the background. And I think I always say my biggest challenge is myself, like, because I know I can do things, but myself just not allowing me to do it because I'm just so scared. So I think that's my biggest downfall in everything, is just to step up, to be more open.
I had two major barriers. One I couldn't control, which is my crappy immune system. So I was sick for most of this. And then my personal barrier was my stubbornness and my pride. Like, I clearly wanted cat food done. That didn't end up happening, which is fine. I'm not very knowledgeable in dogs, and I did learn a lot more. I had a certain mindset towards how data should be displayed and talked about. That didn't go according to plan, and I found out, oh, the way we did it was a lot better for average people to understand it, not my crazy ADHD brain. So it's just getting over the stubbornness.
I think for me, there was, like, I don't have a science background. My background is in history and English and music, and I think I'd be much more comfortable standing up here talking to you about the history of synchrotron and why it exists and how the synchrotron actually works. And so I was worrying about that quite a bit. And then there were some practical concerns as well. Like, can I, like, will I be able to, like, operate the machinery properly? Will I be able to, like, get into various parts? And as Tracy can tell you, and the receptionist, there has been a couple of interesting moments where I kind of get stuck in places in the building because my wheelchair doesn't go that way. So that was fun. But we figured it out and I didn't break anything, so that's good.
Forgot to put the picture of you walking that hutch. I like that one.
Oh yes,
You did it.
I did it, but I was like, I'm very short. So yeah.
Yeah, I'd say mine's science as well. Before first class, I talked to Sharissa and Cassandra. I was like, guys, there's electrons in the syllabus. There's electrons. Don't know anything about them. And I sent Sharissa the admin spot, and I'm like debating it because it's just one spot. I was like, do you want to rock paper scissors for it? But yeah, also got over the mindset. Obviously, the way you approached it with all of us and reminding us all from the start is you don't have to be a science person to be in this class really helped. And got over it and did it and feel pretty good about it. So, yeah.
Oh, okay. Right on time. Our group, we are called the Search for the Spearhead. My name is Danica Krisick. I'm a fourth year education student with a focus in kinesiology and arts ed.
Yeah, hi, I'm Nicholas or Nick Pirelli, if we're friends. You guys can call me Nick. And yeah, I'm like an arts background and some humanities like English, history, that sort of thing.
My name is Cassandra Dick. I'm in my fourth year in the secondary stream in education. My teaching areas are social sciences and English.
Hi, my name is Andre Makatangay. My teaching areas are history and biology, so I have a little bit of science background.
Hi, I'm Colton. I'm in my fourth year. My teaching areas are social studies and science.
And I'm Harriet Pierce, and I'm in sort of my third year-ish with background in English and social studies and middle years.
All right, so our land acknowledgement. We recognize that we are presenting on Treaty 6 territory, and that's the homeland of Métis. And as future educators, we acknowledge the history of this Indigenous land and hope to continue learning and working towards reconciliation. So our project is also kind of based in BC as well, so we have a bit of a land acknowledgement for that as well. We also recognize that the land, our object for our inquiry project, is from and considered Crown land. However, the Metlakatla Governing Council was given 150 million in 2023 as a specific land claim settlement. So we understand that the taking of Indigenous land in the past continues to have implications in the present as Indigenous groups fight for reparations for and taking of their land. We hope that by communicating with one another and attempting to make amends, we might be able to have better relations in the future and grow and better one another. Okay. So, who are we? We kind of introduced ourselves. We have general areas. We are US education students taking ECUR 411, which is an inquiry class. We, for the most part, we don't really have a whole lot of scientific background. I know I haven't really taken a whole lot of science since like high school, a little bit in like 10 years ago in university, but we have a shared interest in like social sciences. So that's kind of where our inquiry project came from, was our shared interest in like history and anthropology.
So to start, the story of our spearhead. In 2010, my family was visiting an island called Digby Island. It's off the coast of Prince Rupert in BC. My brother, who was 5 at the time, we were walking on Casey's Cove, which is a little inlet, and it was low tide, and he found a rock that he thought looked interesting. This is the rock that he found in the end. It's around 11 centimeters, 10 and a half. I was gonna bring it, but my dad locked it in the gun safe for some reason, so I couldn't take it out this morning because I guess it's that important. But it is a spearhead in the end, so that is what he found all those years ago. And the purpose of our project, the ultimate goal of our project, was to figure out the identity of the spearhead and find out what community it belonged to. To do this, we need to understand the people and the place it came from. But how do we do that? So, our hypothesis, the spearhead was likely made by one of the Indigenous groups in the area where it was found. We assumed it was made at Digby Island, and the materials were used that were found there. So, the 3 questions that guided our entire inquiry process were: where was it found / made? When was it made? And what was it made of? These built our entire project, the history, the geology, and the archaeology as well.
So our project is a little different than our other presenter colleagues here. We have a lot of different aspects that don't exactly include the synchrotron or the synchrotron data. We have included it. It is 1 section, but it is part of like 7 sections of our presentation. So we have our geology, archaeology, history. We'll talk about the data. We'll talk about reconciliation, repatriation of our spearhead, and also go through the pedagogy that we've learned throughout this 411 class. So for geology, what's geology? So according to the Geological Survey Island, the word geology comes from, it means the study of the earth. Pretty self-explanatory. So here's a picture of our spearhead. Looks like a rock, right? Comes from the earth. Logical to look into geology, right? So it was found on Digby Island, as Danica said. Here is a picture of little baby Danica and her dad, right? Yes, yep. And this is Digby Island. It's right by Prince Rupert here. It's like in the middle of BC, off the coast, way west. So yeah. So the geology of our artifact, it's made out of basalt. So basalt is an igneous rock, and it's formed from the cooling of magma. So it's like an extrusive one. So it's outside the volcano, right? It comes out, cools outside. So all basalt has silicon, titanium, potassium, iron, magnesium, aluminum, and calcium. Yeah. So, but the big ones are iron and magnesium. So how do we know that it's basalt? We didn't just pull it out of thin air. So we went to a professor at the U of S who's like, he teaches geology and whatever. We had him look at it, and he was like, oh yes, this is basalt. So we had some confidence in it, in our idea that it was basalt. But how would he know? Because basalt has dark and fine grained, so with no crystals, so it's not fancy and cute and all that. It's rich in iron and magnesium, and it has a fine grain to it. So this is how it all compares to like a bunch of the igneous rock classifications. So it's extrusive, like I said. It's outside of the volcano, you know, it's outside, it cools outside there. It's fine grained, so it's not like you don't see really big pieces of it, right? And it's also mafic, which means that it is dark and has a lot of magnesium and iron in it. And so put them all together, you got the solvent. And just comparing our spearhead, this would be our spearhead here to different kinds of basalt. They kind of look similar. There's differences, but there's definitely the similarities there. So how do basalts differ? Like it's a very big overarching kind of rock, right? So we look at the trace elements. There's like little elements that are different in different kinds of basalt. Like there might be in the Pacific Ocean, it might be way different than it is in the Atlantic Ocean, you know, if basalt in those places. So you can differentiate it through trace elements. You can also differentiate it through the concentrations of the different elements in the rock to help you understand about where the rock came from. So here's a geographical map of BC. This is telling us about the geology of it. So there's a bunch of different colors that mean like sedimentary, volcanic, metamorphic, all that kind of stuff, all these different kinds of rocks in BC. Our focus was in here. This is the general area of where Digby Island is. It's kind of close to the mainland here by Prince Rupert. So I zoomed in for you. So this is generally where it was found on Digby Island around Dodge Cove, Casey's Cove. So Digby Island is made up of both igneous rock and metamorphic rock. So the metamorphic ones is the purple and the green is the igneous. And they're both from the Paleozoic era, which is like millions of years ago. So it's not out of the realm of possibility that our rock would be from Digby Island and like taken from it and made there. So it would, you know, the green would be the igneous one. So it could be made from there.
Okay, so like the purpose of our project is to repatriate the spearhead. And so we tried to figure out like which dimensions we could look at to understand where it might have come from. And archaeology is obviously a good place to start, which is the study of the ancient and recent human past through material remains. And so it's really the study of humans, human ancestors, and then all things related to human activity. So it includes things that like ancient humans made, and then also the sites that they used to live on. So we reached out to two people in the Department of Archaeology, and we just kind of took the spearhead to them and asked them some questions. So what was it, identifying markers, how old it might be, and what it was made of. So they said it was an early projectile point. It was leaf shaped, made out of volcanic material, which dated to about 4,000 to 2,500 years ago. That was based on where it was found in BC. It might have been older if it was from other places, but it was because the volcanic rock was available then. And it was made using pressure flaking technique and hafting technique, which was common to people who were living at that time. And so part of the inquiry project is to kind of try to understand how they could look at it and know that that was what they were looking at. So the rock appearance, which was the leaf shape, so the pressure flaking and the hafting, identifying it as volcanic rock and using the location. And then this was just sort of something else to know a little bit more about it, was that the spearhead was found intact, which is very uncommon to find a rock that old intact. It was submerged in water, so there wasn't a lot of residue on top of it to give clues to what it might have been used in. But because it was intact, they assumed that maybe somebody had dropped it or that it was part of a burial. So this is just pictures of like similar spearhead items. And then we have a little video showing pressure flaking. So it's done using a piece of bone, and it's done as sort of a finishing process on a piece of rock. And so you go around the edge of it and it just kind of takes off little flakes of the rock and does it into the shape.
I believe he's using an antler there too. Yeah. And this is with obsidian, so it's a little different than like basalt,
but it gives an idea of what pressure flaking is.
All right, so I'm going to be talking about the history of this, and the reason the history is important is because of repatriating the spearhead. So, who created the spearhead? When was it created? And what did they do with it? Right? So, just for a little bit of background, the tools the early Americans used to hunt were predominantly spearheads, known as Clovis points. And this increased activity means more ground would have to be covered for traveling, because you'd have to chase big game like mammoths and whatnot, right? And this actually made us wonder if the spearhead in question was found from the location on Digby Island or if people traveled with it and it was left there. So the history of Digby Island, it's known as Tsimshian territory. And the Tsimshian group are known for their totem poles and for their matrilineal succession. And the reason we mention, or I mentioned the matrilineal succession, is we want to know if the spearhead was passed down through the generations, through that matrilineal succession. And many outside visitors on the island, the Dene and the Tlingit, most notably, were in conflict with the Tsimshian. And we were wondering as well if this wasn't really a Tsimshian artifact, rather maybe the Dene or the Tlingit brought it there because of some conflict, but they were eventually routed. And now for the cultural significance of the spearhead, it was either Giskin and Tsimshian, but we were leaning towards on the Tsimshian side of it. And it indicates shared cultural or technological influence among the Tsimshian and other groups. And we have to realize that spearhead could have been created in a way where it was culturally significant to the Tsimshian. And the Tsimshian, like I mentioned, were renowned for their applied art. And you could see their totem poles were very intricate. And who's to say that their spearheads weren't created in a way where it was for rituals, for a spiritual aspect. And artifacts such as our spearhead could have been part of a broader cultural expression, such as a ceremonial distribution and gifts, or if it was used in a burial. Now, the historical significance and the spearhead's presence on Digby Island could indicate, like I said, a burial, conflict, or migration. And this can be significant for understanding the spearhead's role in clan rituals or warfare. And the history also helps us determine where the spearhead should be repatriated and who should it go to.
Okay, the data. So of course I'm the arts background, so I'm the best person to go through this with you all. So let's get right into it. Okay, so this is how we scan the spearhead. You saw the little slides for some of the other groups, but we just sticky tack that whole thing right on there. And then we could point the beam at different points on the spearhead to be more sure of our data, increase our confidence. All right, next slide. Okay, so this is our spectra stripped down to the main elements, and I'll show you a more detailed view on the next slide with multiple tests to make sure we didn't get anything wrong. But this is an XRF, which you are probably familiar with from the other groups, but just in case you're not, an XRF involves putting a consistent amount of energy in to see what elements are present. So as you can see here, we've got iron, titanium, calcium, and argon. Those are the biggest peaks. And each peak has a big one and a small one. So again, if we weren't seeing this small peak, we would have to question, okay, maybe something's gone wrong. Is this actually iron? Stuff like that. And then over here is the scatter peak, which just shows how much energy was put in. And I'll talk about on the next slide too. Sometimes there can be elements that we would see in here, but they're swallowed up by this large frequency. Yeah, so we clearly have a lot of iron. There you go, you can see the bromine. The big peak would be here, but we can't see it. So we clearly have a lot of iron, and that is one of the main ingredients in base salt, like Sandra talked about. So we're good there. And one of the other big ingredients is magnesium. There's a lot of magnesium in base salt. Mn is manganese, not to be confused with magnesium. And we couldn't test for that because, as one of the other groups showed on the chart, we can really only hit one row of the periodic table. Magnesium is too light for our beamline to pick up. So basically on this graph, the lower the peaks are, the lower the energy is going to have to be and the harder it is to pick up when we go to Zanes. So what we did end up picking was iron because we've got these huge peaks, and then titanium because it's not as light as these ones down here, and we had a good degree of certainty that we'd be able to pick up something. So let's go to the next slide.
That's me. So my job was to help reinforce the idea that it came from around Digby Island. So I found some XRF charts that have other basalt. This one is found further inland in BC. We can see that there are high amounts of iron in this rock, but there's also a high amount of calcium, which we did not see in our rock. So although there's high amount of iron, maybe not further inland in BC. This one, I found charts from northern BC, but this one's along the coast. So you can see we have a lot of iron in the basalt rocks, and we don't see that high amount of calcium. So I made the educated guess that yes, this can be found along the coast in BC.
Yeah, so from those charts and also the graphs that we had previously, we're seeing elements that should be present in basalt. So that's supporting our hypothesis so far that it is basalt, right? Okay, so here's our zanes, and this was my biggest barrier to preempt a question from Tracy because it involved using Excel, and I hate Excel, which is something I learned. So this is zanes. So the difference between zanes and XRF is zanes involves putting a varied amount of energy, and it's not just one consistent amount. We're slowly adding until we see the edge here, which is this big spike, and that is telling us the speciation or the type that we have. So for iron, this is showing us, if we go to the next slide, because it looks pretty similar to the iron 2 we have on this graph, and on this graph, this is just another iron graph, we can be reasonably confident that we do have iron 2. And iron 2 is ferrous iron, which means it's in an oxygenated environment. And as we know, this is supposed to be an extrusive volcanic rock. So it makes sense that we don't have ferric iron, which is in an oxygen-deprived environment. That would mean that it had to come from deep underground and be mined out or something, which, if indigenous people on the island made it, they would have found it near the surface. So far, so good, right? Next slide, please. Okay. Okay, yeah, so also something to mention about those previous graphs. They're not about basalt specifically, but the graphs look similar, so, I believe that they still apply. So don't get mad at me. Okay, so now we're gonna see if the data makes sense, right? These gray dots here are iron deposits along the coast of BC, and that circle is right where Digby Island is. And then these dots are different elements. So we see that there's a lot of iron there, and there's a lot of iron in our sample. So again, so far, so good. It could be from there, that's possible. Next slide, please. Okay, so this is our titanium zanes, and this looks a little less smooth because, as I mentioned, it's a lighter element and it's harder to pick up, and we had less of it. So as you can see here, the edge is right there about 49.75 on the x-axis, and it doesn't look quite as good as the other graph. But if we go to the next slide, we can see that when we look at titanium, what is it called? Oxide. When we look at titanium oxide, it looks similar. So the blue one up here. And actually, these all look pretty similar. So we could have a good degree of certainty that this is what we're looking at. However, titanium 3 is titanium chloride, which is typically unstable and produces hydrochloric acid, I believe, from my readings. So yeah, we probably don't have that one. It makes sense that we've got titanium oxide because it was surrounded by oxygen. Yeah, and it resembles the titanium oxide a lot more than the titanium metal. It doesn't quite have the same peak that this one does. And then here's just another example. Again, we see the first peak's higher and then it dips down and does a secondary peak. And again, that looks similar. And these graphs actually were from basalt, so we can be even more sure than we were with our first round of graphs. All right, so let's check again if our data makes sense. We gotta make sure, people. Okay, so BC mines mostly consist of copper, lead, gold, silver, and limestone. And there's actually very few metal mines in Canada. Along the coast of BC. As you can see, there's a lot of oil and stuff, Alberta into the eastern side of BC. But these are really the only mines that it could be from, and none of them have titanium. Most of the titanium mines are actually from Quebec. So we know we had a low concentration of titanium in our sample, and it seems that BC doesn't have a lot of titanium. Therefore, it does not rule out the spearhead being from BC again, which is good news for us, because if this ruled it out, we'd be in trouble. This is kind of towards the end.
Okay, so in the end, reconciliation, returning the spearhead to where it belonged. We got all our data, we got all our information, but what do we do with it now? So to start, we've talked about a couple of the groups that are in the area, but I used nativeland.ca to kind of figure out more about how many different groups were in the area. So this kind of shows them overlapping. This one just kind of shows it has a little line there that you can't really see. But this is Dodge Cove and Prince Rupert, and there is so many groups in the area. So the first group that I reached out to was the Gitskala, because I believed they had a museum in the area that, though we didn't believe it may be from them, I believe they could have led us to something. So it involved a lot of emails to several specialists and museum curators in the area. The first group, as I said, I reached out to, I linked to their just general email. I said, we found something, what can we do with it? So I contacted the local museum. They're a little further. So this is Prince Rupert, Dodge Cove is, Digby Island, sorry, is right over there. Their land is a little further, but their museum is still in Prince Rupert. So I thought it was a good option to reach out to them. The members of their team then contacted the manager of their culture and language department, as I then provided photos and a story to back the first email, as I didn't know anything to provide in the first email besides we have a raw, what do we do with it? So they then contacted some other people in their team linking to, we would like to give it back to the group it belongs to. They then contacted the Museum of Northern BC, as they believed the group belonged to the Tsimshian, which was, with our information, we did believe it belonged to them. I did not know they had a museum in Prince Rupert as well. I thought that museum was more general, but it is the group, that's their museum. It's right next door to the other one, actually. I didn't know that. But they believed it belonged to the Tsimshian. They then contacted another member of their team who worked with Recreation, and that's where we're sitting at right now. It's been 2 months. I found out the museum's actually closed in off season because they don't have enough people to visit and enough staff to work. So maybe when the summer hits, we'll reach a more conclusive in returning the rock to the people. They were very interested in it, as they have many others, they said, from the area. They led us to telling us about how Digby Island was a winter camp for their group and everything. But the emails kind of just burnt out at the end. So in the end, who should we return it to? If they don't want it, they do want it, but if we can't get it to them at the moment. Our conclusion, though, is that the rock is basalt. It's probably from close to Digby Island, and the Tsimshian likely created the spearhead. We base this on the history of the Indigenous groups in BC, the geological and tool-making history of the area, and the advice of the experts and the data received from the sacred fossil. Our hope is to one day be able to give the spearhead back to the people and the Museum of Northern BC, as we believe that recreating items from Indigenous people is an important step in reconciliation and showing respect to the Indigenous people of the past.
Okay, so we're going to talk a little bit about the pedagogy, and there's sort of 2 dimensions to the pedagogy. There's the learning that we had, and then there's the learning that we think could go into the classroom. Okay, so the pedagogy of our learning. So one thing I thought was a new experience for me is I've been in classes where we formed groups and then chose a topic, and I've also been in groups where the topic was assigned, but I've never been in a situation where it was more of a choose your own adventure, where everybody sort of brainstormed ideas and then got behind the ideas that they thought were the most interesting. And I think that because of that, it seems like other people experienced this too. We were all pretty enthusiastic the whole way through because we were so engaged by our own topic. So that was something I thought was really interesting. And then contacting experts, like most of us have never really had a lot of experience sort of cold calling profs and other departments, just being like, hey, look what we have, can you tell us about it? And it was really exciting. And it was kind of cool to like touch base with people who were also really excited to tell us about what we had.
The history, we did a lot of like our own research, so we each kind of chose an area that interested us the most. And that was kind of interesting. So like I took an archaeology class, so that was a natural fit for me. Andre does history, like everybody kind of picked, well, Nick, his arts background obviously was a
Woo! Yeah.
connection to science, but it allowed us to sort of come at it from different angles. And then of course the scientific process, which none of us were super comfortable with, but I think we all found super rewarding.
I'm back. Yeah, actually, I want to jump off Harriet's last point. Like, when you're in a group and everyone kind of has their areas of strength, as some of the other groups talked about, not all your bases are probably going to be covered. So, you know, some people have to take it upon themselves to step out of their comfort zone. And group work is just one of those things that you have to practice to like keep up your skills at, right? Like compromise, all that stuff. It doesn't really get easier the more you do it. You just have to remind yourself why it is valuable. And you know, we have to have good communication while we're doing this because there's so many of us in this group and there's so many different sections that we wanted to cover. So we had to make sure, you know, we don't want to be repeating ourselves too much. We want to make sure it's clear, you know, who's covering the introduction, who's covering the conclusion, all that stuff. And then also just like, you know, scheduling stuff, like, can everyone make the beam time? You know, there's lots of moving parts. And yeah, like, obviously this is going to be important as we move into the professional world and have to worry about like 30 kids, you know, and not to mention all the other staff. And then I want to talk about guided inquiry a bit. So what we did in the class was Tracy gave us a combination every week of assigned readings and then some readings that we could pick from. And what I really liked about this is that Tracy did something very sly and she picked some readings that she didn't actually like or agree with or thought there were problems with. So in that way, it wasn't just that let's all make sure we echo what Tracy thinks, which, you know, obviously I didn't because I'm kind of a contrarian, as Tracy now knows. But it's great to be able to think for yourself and take what you do like and point out some of the things that you don't like, because not everybody is going to take away the same thing, right? So even if there's a reading that Tracy really did like, you know, maybe that one didn't connect with me, but the other one did. So I like that we had options, and I'm stealing that from my class. You'll be happy to know. And then one of the other parts about it was the synchrotron was just the guiding piece, right? So every group did use the synchrotron, but we were interested in this spearhead and you know, history and anthropology more so. So we got to use that as a piece of it, and it was kind of a guide rail, but it wasn't the be all end all of our project. So if we didn't get anything super conclusive, which we didn't, it didn't rule it out, but it didn't rule it in per se. We still had all this other stuff to fall back on. And then the experts, like when we were on the synchrotron, we had some wonderful people there to help us out and give us a little bit of guidance, right? But the same thing, like throw the ball and go figure it out, you know, like this is your project. So that was really cool. And we got to draw our own conclusions and analyze the data on our own. So there's the opportunity to make mistakes. And I think we do need more opportunities for people to make mistakes, so we're not so afraid of failure. But that's just, I'll get off my soapbox now.
All right, and also we bringing it into the classroom of like our students, our future students. There's also things that we can take away from this 411 class into cross-curricular teaching, because our whole group had a lot of like geology and archaeology and history and like using the data, which is like very like cross-curricular, right? And we can take that knowledge into our own class and like implement that for our students and like encourage them to think outside of like just like the math that we're doing, take in other subjects that we're also teaching. We also want to like encourage scientific study and independent research. So I think this was like a good example of how we experienced it and how we can help our students also experience it. And we also learned how to get information. So all those contacting experts, like the geologists we talked to and the archaeologists that we talked to, and like that experience, I think helps like heighten how you can help your students also ask for help. Like you don't always have to come to the teacher, you can come to your peers, you can come to other teachers, you can reach out to other people in your community. So I think that's a really good experience to like impress onto your students as well. And these are our references. We have a lot.
Tracy
And-
told me to make them small.
So they are very, very small, but for people watching at home, zoom in. And we'd also like to throw out a special thanks to Tracy for teaching our 411 class, for Dallas at CLS for helping us with our helping us guide our inquiry, for Glenn Stewart, who was and Terrence Clark, who were the archaeologists that we contacted at the U of S. Val Masters, who is the collections curator at the Gitxaala Nation in BC, and Kevin Ansel, who was the geologist we also contacted at the US, and everybody else that helped us at CLS. That helped us with like the scientific stuff that we had no idea about. Thank you very much. It was much appreciated. Any questions?
I have a question. What program was it? Just Google Maps that you used to look at all the iron and the TV and stuff, or what?
So about the specific mines was there's like a government website that shows all the different mines and different types of mines. So like I sort of had that legend on the side showing the types, but you can like click on that and go more in depth, or click on a location if you want more information about what they specifically export, but like refineries and stuff too.
If I remember about the iron and like the gray and the orange dots, I think that's from also like a government website. I'm remembering right.
And the geographical map was also a government website.
Shout out the government.
It worked.
Yes.
So I have a couple of questions, and you might have thought about this, but I didn't hear it as part of your presentation. In terms of time and space, you seem to have a very static view of this artifact, right? Because I look at it as if people have boats and a coastline, you can trade as far up as the ice pack and as far south as you can possibly go. So why were you limiting the idea of, I mean, first assumption was it's from that island. I think you need to think about what assumptions are you making about the people who actually made that. So that's question number one. Question number two is you also have a very static view of what nations were living in that location 2,500 years ago, because you talked about essentially nations that currently exist. So, you know, I'm from England. If you find a spearhead from the place I was born in England and you're trying to figure out how to repatriate it, you can't, because none of the people living there, they're all gone.
I would like to take a first crack at these, I guess. There's a lot there to go through. Yeah, so I think like part of it is that it's fairly remote, right? And the other part is, so like, as we did talk about, like there are groups that move through. And so while we can't definitively say like it was from here, it was made wherever, and then it moved to this place because of X, Y, and Z, it's not out of the realm of possibility that that type of rock was found there, that the people who were living there at the time, because it's my understanding that that group moved away from the island after a while, but that technique is consistent with what they would have used. So it's kind of just putting the puzzle pieces together to say, it's not unlikely that it is from where it was found. But yeah, like, again, like, because I don't know that much about science, when we were using the synchrotron, I was like, oh, like, you know, maybe we can like find out what element is in it, and it's going to be like zutonium, and zutonium is only in the north, and we know it's from there, you know. Unfortunately, we didn't get something that definitive, but, you know, as the other group said, like, just because you didn't get something you were hoping to get doesn't mean that you got nothing, right? So and I think a lot of science kind of operates along the like, this is our working theory until we're proven wrong. So, you know, for us, yeah, you know, if we had more time to go into more depth, maybe we would find something to prove us wrong, but, you know, that's just our hypothesis for now.
I also wanted to jump on it and say, something I never mentioned that is a part of this was one of the archaeology professors that we went to, his actual degree, he got his PhD doing archaeology on that island. It was very lucky that he is at the U of S and not in BC, where his research was done. But there is a quarry there that they have done archaeological digs on. He said that the rock looked very similar to the ones found there. That's why we were very sure about the date and everything, is because of the quarry that he said he was like, oh, you found it on Casey's Cove. I thought you would have found it more inland. So there is a quarry there. They have found multiple artifacts that look very similar. So we were kind of also going off that basis that, like, because there's been other artifacts found from those nations that we mentioned, they were probably also in the waters nearby.
Does that help? You're good. Okay. I'll let you off.
Dallas. I just want to give kudos to this group. I think it was pretty early on in your ideation that I kind of poked a hole in the theory of like, who owns this, and you guys met that challenge. I get nervous calling my doctor, so the fact that you guys are calling all these experts and stuff, that's pretty remarkable. And so I hope that there's a conclusion to all of this, and if there's anything I can do to help support that, I'm part SimShade, so I'll take it off your hands. No, I'm just kidding. But kudos. I just want to say it was a great, for me, an exercise in thinking about that and logistics. So yeah, really good.
I'll have to get into the gun safe first.
It's heavily guarded.
Okay, so here's your curveball.
I'm ready.
If you were to approach this project or something very similar again, how would you go about it differently?
Is that as a current?
I mean, it. Wow. I think, like, you know, stop me. I think that it would have been helpful to, like, now that I understand like what that beamline specifically is actually capable of, to kind of temper my expectations about what kind of data I was going to get out of that. And so maybe we could kind of focus more on some of the other areas earlier, or maybe even like try to get more in depth with like basalt composition and all this stuff. So if there was a way to make it a little bit more definitive, you know, because really the data was just like, well, yeah, it seems like it sort of goes with what we were thinking. So I guess so. So I mean, that's probably what I would start, is like dig more into like the details of basalt and all that.
I feel like if we had like more time to like look into like the geology of it, like the composition of it, I think that would be kind of interesting. I would also, you know, even we jokingly discussed it, but like going to BC would be kind of cool. like actually doing all this stuff, which would be like more cost and like more time and stuff. So yeah, and like I would probably like hurt my expectations when I went in to like talk to the geologist. I was like, maybe we could even like find what mountain it's from. So, that did not happen. Yeah, maybe going in with like more realistic expectations would be good. So,
and to add, like, if we did have like a lot more time and all that stuff, like to actually maybe we could actually get another spearhead that they knew was from that area and test it against each other. To see that everything matches, because we only had the one spearhead, and we had some other like basalt from the area to test. But we thought that it was, you know, a better use of our time to instead do the multiple zanes on this one. So that would probably be where I would go with it.
And we didn't have the time on the line to like test other basalt. Actually, the archaeology professors were like, would you like some spearheads from Saskatchewan? We're like, well, I don't know if that'll help us, if I'm honest with you. So yeah, anything else?
Okay. All right, so I just want to thank everybody for your time, for joining us today. I want to thank all of the students for your hard